So in the last section, we learned what the eigenvalues and eigenvectors of a matrix are and how they relate to that matrix. But how do we actually find the eigenvalues and eigenvectors of a matrix? So to do this, we're going to go back to the definition of what it means to be an eigenvector and eigenvalue. So x is an eigenvector and lambda is its associated eigenvalue if this equation holds for a non-zero eigenvector, right? All right, so how can we use this to help us find lambda, find x? Well, what we could do first, we're going to move lambda x to the other side of the equation. So we'll get ax minus lambda x equals the zero vector. Okay? Now, our initial thought might be to factor out vector x here. The problem is this isn't actually well defined. A is a matrix, lambda is a scalar. Matrix scalar subtraction isn't well defined. We don't know what that means. Okay? Distribution or factoring in this way doesn't make sense. But fortunately, there's a fairly straightforward workaround. So what we're going to do is we're going to use the power of the identity matrix here. So that is vector x is the same as the identity matrix times vector x. And now by just squeezing in the identity matrix here, now if we factor out vector x, it will make sense. Because now we have a matrix minus another matrix. And matrix subtraction is well defined. That does make sense. Okay? So notice what we have here. We have a matrix, which is a difference of two other matrices. But if you take that difference, if you subtract them, you get a single matrix right here. So we have a matrix times vector x is equal to 0. Okay? Now remember, an eigenvector has to be non-zero. So this homogeneous system, we're interested in when it has a non-trivial solution. We have a eigenvalue eigenvector pair lambda x if x is a non-trivial solution to the homogeneous equation a minus lambda ix equals 0. Okay? So our goal here, our first goal here, is to find for what values of lambda does this homogeneous system have non-trivial solutions. Okay? Now, if the system has a non-trivial solution, that means this matrix in reduced row echelon form would have a free variable, which means it would have a column without a leading entry, which means that because it's a square matrix, there also must be a row without a leading entry. The only way that that could happen if you're in reduced row echelon form is if you have a row of zeros. Okay? So if we have a row of zeros, that means that the matrix is singular. So that gives us a way to work this out. This system will have a non-trivial solution if and only if A minus lambda I is singular. Okay? Now we can test if a matrix is singular. One way that we've learned is by taking the determinant. So we want the determinant of A minus lambda I to be 0, because we know that any singular matrix, the determinant of any singular matrix is 0. This actually gives us an equation for solving for the eigenvalues of the matrix. If we could find all values of lambda that make this equation true, then we will find all eigenvalues of the matrix. We call this equation the characteristic equation. Characteristic equation. The solutions lambda to the characteristic equation are the eigenvalues of the matrix. Okay, so that gives us a way to find the eigenvalues of any matrix A. Just plug into the characteristic equation and solve. All right. Now, right now it doesn't look like it, but once we see this in action, once we actually take the determinant, find matrix A minus lambda I and take the determinant of the resulting matrix, we will see that we get a polynomial equation. Solving that polynomial equation will give us the eigenvalues of matrix A. Once we find the eigenvalues, then we will know A minus lambda I, the different values of lambda that we would want to plug in to find the eigenvalue eigenvector pairs. Once we know the eigenvalues, we could plug the different eigenvalues in one at a time and then solve each homogeneous system for each eigenvalue. Once we know the eigenvalues of A, we can solve actually, let me write, we can plug in each eigenvalue one at a time into the equation A minus lambda ix equals 0 and solve for x. Okay, now, so once we know lambda, we can plug in the actual particular values of lambda here. That's our strategy. And then we will solve this system. It will be a homogeneous system. But also, we are choosing the values of lambda so that we will have non-trivial solutions for x. That means infinitely many solutions. So we often talk about the eigenvector associated with eigenvalue lambda, but really it's a family of eigenvectors. In fact, every x that solves this equation would be part of the null space of A minus lambda I, right? Every eigenvector solution of A minus lambda I x equals 0 is part of the null space of the matrix A minus lambda I. That's what it means to be in the null space, right? It's a solution of the homogeneous equation involving that matrix, okay? Which means that the set of all eigenvectors is a subspace. and I should probably say associated with an eigenvalue. Different eigenvalues will have different eigenvectors, right? Associated with an eigenvalue is a subspace. We call the subspace associated with eigenvalue lambda the lambda eigenspace of the matrix. And write and notate it S sub lambda. Okay, so the set of all eigenvectors is a vector subspace. The set of all eigenvectors associated with a particular eigenvalue, we call it the eigenspace. The eigenspace is just all the eigenvectors associated with a particular eigenvalue.